The purpose of this webinar is to give you an overview of sort of from start to finish how to estimate a placement algorithm, starting from collecting the data, what sort of decisions have to be made, and the actual estimation, which we'll just do some basics there, and understanding some of the limits and extensions, how to take this further as well. So feel free to, I'm used to having people interrupt me with questions as we go. So if there's sort of clarifying aspects that you want to ask, do feel free to speak up. Alternatively, I'll leave some time at the end to answer any questions you may have as well. So feel free to write them down, but whichever is helpful for you. All right, so just to get started with some of the goals here, the first thing we're going to cover is understanding what the algorithm does. What's the output going to be, how it works and such, and then discuss what data is needed to estimate the algorithm, how we organize those data as well. We'll go over some basics for estimating an algorithm and understand what it takes to update it. So for instance, if you either get additional years of data or you want to introduce new variables that we weren't using in the current algorithm that we've estimated for the colleges. All right, so moving along here. So to give you just a basic reminder of how the algorithm works, essentially what we do is we start with data from previous cohorts. So this is the historical data, which many of you probably were part of providing to us. And with these historical data, we had students, their placement scores, their high school GPAs, and we had their grades in their college courses. And we could use that information to develop a formula to predict how well they are likely to do in these college courses, using data from incoming data, sort of their GPA and placement scores and such. And then once we have that for the historical data, we can use it to place new students. So we get the same information from students as they come in, and we can use that to create a decision algorithm that allows us to place new students. So that's what we'll be going over, all three of these aspects today. So moving along in terms of designing the algorithm. So what does the algorithm give you? So what it's going to do ultimately is give you a predicted likelihood of success. And I put success in quotes here because we'll actually have to define what success means. And I should say we'll also be able to share these slides with you. So just as a heads up, if that helps. So for a given student with certain incoming characteristics, what is the probability that they succeed in a college level course? So for instance, the probability that they are likely to pass a college level course, get a C or above. And so one of the first decisions that has to be made is defining what is the outcome we want to predict here. So how do we want to define success? And colleges might make different decisions here. So for many colleges, this was passing a college level course, for example, getting a letter grade of C and above. What's important is that we define success as binary, so a 1 or a 0. So either you get a C or above or you don't. And that's how we're defining success in this instance. And what the algorithm will then do is it'll spit out a probability that the student receives a C or above in a specific course. And so that's the other facet that as we've implemented it, is we define success for each placement that the student has. So we'll have getting a C or above, for instance, in their first college level math course, or getting a C or above in their first college level English course. Those are separate definitions of success, and we'll have different algorithms for each of those subjects. So that's an important facet here as well. In theory, you could even have different thresholds for each college level course that you want to predict. I think in practice, and we're going to query the colleges about this, that it was mostly a C or above that we used as the indicator, but we haven't gone back in the records to confirm that that's the case. In any case, it'll be the same process irrespective of how we define success, as long as it's this C or above, D or above, or even B or above. So that's the first decision that has to be made here. And then the second decision, the second facet is what can we use, what data can we use to predict this likelihood of success? And the important aspect is, all of this has to be data that you can use at the time of placement, right? So, and this is not trivial, as you know, because we want to, for instance, get high school GPA. That's not always available right at the time of placement, so we have to make sure that those processes are there such that we can collect those data that we're going to use at the time of placement. One other nuance here is we want variables that predict the likelihood of success, but we don't necessarily need these variables to be causal. So, when we look at the coefficients here and we see what the values of these coefficients, it doesn't mean that we think that, for instance, these test scores or their diploma status has a causal effect on their likelihood of success, but we do think it's predictive, it's associated with the type of characteristics that seem to predict success. So some of the variables that we've used are high school GPA, diploma status, for instance, GED or otherwise, their time since high school graduation, their placement scores, and in theory, we weren't able to use this, but we've seen in other places they've been able to use for instance, their last math grade in high school as well. But again, the key trick here is being able to get that data right at the time of placement so that it can be entered into the algorithm and place students quickly. Some important constraints. As I said before, we must have these variables in the historical data. To give you an example of how that can be a challenge, for instance, having high school GPA wasn't necessarily readily available in the historical data. Even more challenging would be if you wanted to incorporate, for instance, a non-cognitive measure. So say you wanted to do a survey on students' grit and then incorporate that into the algorithm. The key issue is you need to have historical data with that measure of grit and observing students' grades in their college level course. So if you were to implement a new measure, and we'll talk about this towards the end of the webinar, you'd have to collect data on that measure of grit and then watch those students until you can observe their grades in their first college level course. So we'll come back to that question about incorporating new measures, but I wanted to make that clear here with the historical data as well. Let me just pause and see if there's any questions about that. Again, we'll come to the updating soon, but or later, but just to make sure there's no questions about the historical data aspects here. Okay. So the other aspect is to be sensitive to what you put in the algorithm. And so what do I mean by that? For instance, we don't put any demographic variables in the algorithm. So certain race, even gender variables might predict likelihood of success. Again, we don't interpret these as causally having an effect on success, but nonetheless, they could be predictive. But, one has to be sensitive, obviously, to what you want in there and what sort of the coefficients that might be associated with certain demographic variables. So we excluded those altogether, even though they might have predicted value. And we think that's appropriate, but just wanted to highlight that aspect to you to be sensitive to that. And in theory, sort of what goes into these algorithms is public information in a lot of ways, especially students probably have a right to request what's being inputted into this. So think of that as you decide what to keep in the algorithm. Okay, so setting up the data. So, and by setting up the data, I mean setting up the historical data so that we can estimate an algorithm here. All right, so what we need are these elements for each subject. So for each subject that there's going to be a placement, we'll need these data. And the data have to be at the student level. You want to restrict to students who have, and this is for the purpose of the historical data, or for what the algorithm is estimated on, is students who have taken a college level course in the subject of interest here. So for instance, you want to make sure that the algorithm will be estimated on students who have taken the college level course in math, if you're going to estimate the algorithm for math class. and similarly for English. So you're actually going to have separate historical data sets for each subject here. So within those historical data, you'll want to observe their grade of their first college level course taken. You'll want to be able to link that to their incoming student characteristics, such as high school GPA, diploma status, their test scores, etc. And then, of course, there's a question of how many years of historical data does one need to estimate an algorithm. And unfortunately, there's actually no clear or sort of absolute answer here. And in practice, it probably depends on what the size of an incoming cohort is. So if there's small cohorts, quote unquote, then one might need more historical data. We typically use 3 years of historical data to estimate the algorithm, which we thought worked pretty well. And what we'll be able to do is discuss ways to look at how sensitive placements are to having more or less data. So there might be some ways to get at this to understand how sensitive the algorithms are if you only have one cohort or data or two cohorts, things like that. You can basically see, well, how much do the coefficients change in the historical data? Using coefficients change if we only use two years versus 3 years. How sensitive is the algorithm to this? And then, as I mentioned before, we want separate data sets for each subject. So you can think of each analysis here, each algorithm is just a totally distinct process. I think that's the easiest way to think about it. Any questions about that? Yeah.
Did you take into consideration students who may have taken remedial courses?
So how do you mean take into consideration?
Well, if a student, if you're looking at historical data, there could be students who, before they take a college level English or math course, they actually went through remediation and then went into the course. And so the remediation may have had an impact on their outcome, and it doesn't sound like that
No. That you make a great point, and that's actually my mistake, which I should correct. So you're exactly right. What I should say here, and I'm going to try and correct this on the fly, is we want students who took the college level course as their first course, if that makes their first course in that subject. So what we're trying to do is mimic students the idea that we want to look at predicting the likelihood of success for students who took a college level math course as their first course. Does that make sense or clarify? That's totally my fault. Does that answer your question though?
It does answer my question.
Yeah. So because you're exactly right for all the reasons you just pointed out. So I'll just write this in, and we'll adjust this a little more formally in the slides here later. Yeah, thank you for pointing that out. That's important. Okay, great. So any other questions related to that? Okay. All right, so setting up the data. We usually received a couple of data sets. So often we would receive one data set which was the transcript information for each student. So we would have every course that students took once they were enrolled in college, all of the grades for those courses, and what the subject titles were so that we could identify which were the first college level course that they took. Then we would have another data set which was the student's incoming characteristics. So this might have their high school GPA. Often it would have a lot of demographic information, which we wouldn't use for the purpose of placement and financial aid information, but it would have their diploma status, their GPA, their time since graduation. Sorry, was there a question there? Okay, so then what we would do the idea is to link these two data sets so that we have one row per student in each data set for each subject. So again, think of this as a separate analysis for each subject. So with the transcript data, what you would do is take the, you're going to take one observation per student from that course transcript information. Even though there's all their courses, you're going to pull for instance, let's pull the students who have took the college level math course as their first course. We're going to pull that student and their associated grade. And so then we've got one row per student per subject in the course transcript data, and we can link that to their incoming student characteristics as well. And so in the end, we'll have one row per student that has the outcome, the course grade. It also has their incoming student characteristics. And in theory, we can do this for multiple cohorts. So in our case, like I mentioned, we did this over 3 years, fall, summer, spring. I think, yeah, fall, spring, summer. And then we would do the same thing again for English. So we go back to the course transcript data. We would pull out all the students who took college level English as their first course. We would pull the course and their grade from that data set, and we would link it again to the same incoming student characteristics. So now we'd have two data sets, one row per student. They would have their course grade, which is our outcome for each subject, and then again linked to their student characteristics, and we'd have that for 3 years, math and English, separate data sets. And then the other facet is we want to make sure that we restrict the data to all those who are eligible for placement. And so the idea is that the algorithm is going to replace students, replace the placement mechanism for those who are taking the exams or who you want placed in this process. But if you have certain exemptions that you want to maintain, then exclude those students from the data. We sort of don't want their characteristics to inform the algorithm if they're not going to be part of the placement process. And so I'm sure you could imagine maybe there's certain exceptions that we made for students with usually small numbers of students with certain incoming characteristics. I can't remember what these were off the top of my head, but there might have, for instance, in some cases been restrictions associated with students' English language learner status, things like that. They just had a separate placement mechanism that wanted to be maintained outside the algorithm. So we want to restrict to all those students who are eligible for placement in these specific subjects. Does that make sense? Yeah.
Could I ask
Please.
another question? When you refer to eligible for placement, does that mean the ones who we require to take the placement test?
So that's largely how we had defined it in coordination with the colleges. But I should say, it's really up to you. Basically, what I mean by this is all students that you want to be placed by this algorithm should be in the data. Any students that you don't want to be placed by this algorithm, you should remove them from the data so that they don't inform the coefficients of this algorithm.
Okay, but I guess I'm a little unclear, and I'm maybe haven't thought this through, so I'm kind of thinking out loud here. How well does the placement test score actually function in the algorithm? Because if somebody, for lack of a better term, fails the placement test, they will obviously not have gone into the first level college course. So the range that you're dealing with are, if I'm not mistaken, given what you said, is, sort of the passing range of the placement test.
Yeah.
So
this is a great question, and so I have a slide on limitations at the end, and okay. This is one of them. So what you're saying essentially is there's sort of an extrapolation problem here where we don't observe. Ideally, we would have data on every student taking a college level course, and we'd have so that there's no kind of restriction on the placement scores that we would see. So I'll just repeat your question once more, and you can correct me if I'm not repeating it correctly. But basically, you're saying given that we're restricting the data to those who take the college level course first, that means that these students largely have sort of passed the placement exam, meaning they've scored above a certain threshold. So we won't observe students with, for instance, very low placement scores in the data. And so when we're correlating the placement scores with their grades in the end, it's sort of on a restricted sample, and it might not provide as much information as it could if we saw everybody's placement scores and correlated that with their college level grade. And
right.
Yeah, so what this is kind of an extrapolation problem where we don't observe everybody's placement score, so we're sort of extrapolating what would happen if there was a low placement score based on those who actually did pass. This is potentially an issue. It turns out with the AccuPlacer scores, they have very low interreliability, meaning that if a student, and maybe some of you know this better than I because you see students retake the exam, if a student takes the exam multiple times, their scores can actually be quite different. And for the purpose of placement, that's actually not ideal. For the purpose of the algorithm, it's actually helpful because it means that we're going to observe students whose, one could imagine that, if they took the exam multiple times, let's say hypothetically we had a student whose true score, as though they took the exam, 5, 10 times, their true score might be high, but maybe they just got a bad draw and, bad luck taking the test, and, we observe their score going in as well. So the fact that the scores are kind of noisy, meaning they have a lot of variation, actually helps us here. And Judy Scott-Clayton, in her paper, which we can send along, which is the basis for a lot of these analyses, she goes over this aspect of extrapolation a lot and finds that in this particular instance it's not as much of an issue as it might be. But in general, your question is spot on and is definitely a potential issue. In the end, you'll see how well the AccuPlacer scores correlate. We've done this both on the restricted data, where we look at only those who pass, and those who, we just look at their AccuPlacer scores correlated with other outcomes, irrespective of their first placement. In general, we find that once one conditions on high school GPA, the AccuPlacer scores don't predict a whole lot regardless, actually, even, unrestricted or restricted samples. So let me just pause there and make sure that I, one, answered your question, and two, if there are any other questions.
No, yes, you did answer my question, but I just want to mention that, the experience that we've just had with you in terms of using the algorithm along with knowing what the placement test scores are, it gave us the opportunity to look at how students do who, if they had only taken the placement test, may have been put in remediation but weren't because of the algorithm. And so that, to me, was very exciting data because it shows us what happens to students who we would have put in remediation, but they went in, and it turns out that, they really performed at, comparable levels to students who did pass the placement test and went into, college level. So this was one of the rare times when we had that kind of data, which I thought was really interesting.
That's great, and very glad to hear it. And I should say that that's exactly. I just saw a question pop up. That's exactly the sort of analysis we'll be doing too. So we'll actually be looking at the subset of students whose placements were changed as a result of the algorithm relative to the placement scores, the business as usual, and we'll look at the outcomes for those students and be able to provide you evidence on that. Obviously, we have to wait a little more time to make sure that we can observe everybody going through the college level courses to give an answer, but that's exactly what we'll follow up on as well. So appreciate that. I think I also just saw a question that, if I'm remembering right, was, does this mean that the high school GPA is a better predictor than the AccuPlacer scores? Did you see that question come up? Oh, okay. Yeah, so I think I saw it pop up, and somebody can correct me if that's wrong. The short answer to that question is yes. The high school GPA is a much stronger predictor in terms of the measures that I'll show you shortly than the AccuPlacer scores. And the general rule of thumb that we found and others have found as well is that grades tend to predict grades very well. Test scores tend to predict test scores relatively well. And so this is true in this instance with the colleges we worked with, where GPA and course indicators are stronger predictors of future course taking than the test scores. And this is true not just in the settings that we worked with, but you can find several papers showing that high school GPA is a predictor in all kinds of different four-year colleges, and even in comparison to SAT scores and things like that. So this seems pretty uniformly true that high school GPA is an excellent predictor here. Any other questions before I move on to one other slide here? Sorry if you're seeing some of my other notes pop up. Okay. All right, so initial coding, once we've got this data set up here, so essentially what I'm saying where we're at now is we've got a data set where there's multiple cohorts, so we have several years of data. We've got one row per student with their outcome data and their incoming student characteristics. So we've got their course grade in a subject, and we've got their incoming student characteristics, GPA, diploma status, et cetera. So how are we going to code all of these variables? Well, I can give you an example of how we've coded these data. It's not necessarily the only way, but I think these ways make sense. So first, as I said before, we're going to code the outcome as a binary variable, an indicator for passing or not. So for instance, getting a C or above. So that's how we code the outcome. Depending on the system, we can leave high school GPA as a continuous variable. And one issue that we ran into is that some students come in with GPAs on a 4-point scale. It seemed like most students came in with GPA on a 100-point scale, more or less. And one easy way to handle this is actually to create just separate variables for each if you don't want to try and translate the scales. So you might have a high school GPA 4 as one indicator, and then a high school GPA 100 as another variable. And for students who have the 4-point scale, the GPA 100 variable is just missing for them, and you can have an indicator there. And for students who have the 100-point scale, the 4-point GPA that variable will be missing for them. So you can just create two variables. Alternatively, you could try to put them on the same scale, but I don't think there's really a need there. It's not so essential. Again, the goal here is prediction, so I think keeping the two variables separate actually works pretty well.
I got a question.
Yeah, please.
So our school is dealing with, we have 3 different scales. We got a 5-point, 4-point, and a 100-point scale. Obviously, introducing or keeping the things separate would introduce a lot of missing data variables, missing data in those columns. Why do you recommend not recoding the scores?
Yeah, so it's a good question. So like you said, it introduces missing data, but this missing data actually isn't really an issue here. So I'll come back to this slide, but let me tell you what I do with missing data, because I think this might help answer the question. So I'm going to go ahead one slide to what to do with missing variables. So what we do is we impute the variable, missing variable with the mean, or actually what we did is imputed it with zeros. And at the same time, that's probably going to seem weird to you, but I'm going to explain why it's actually not so strange to impute it with a zero. We create an indicator for that variable having a missing value. So now we have two variables. So we've got, let's say, high school GPA. So we've got the high school GPA is missing, and then, so we've got high school GPA, and it's got values for students have values, and then it's got zeros for students who are missing it. Then we have a separate variable which is high school GPA missing, and that's an indicator for having that variable missing. And it turns out including that indicator for missing means that you can, the value that you impute the other variable with doesn't matter at all. So I could make it 0, I could make it 10,000. It won't change the coefficients at all because we've sucked up all that information with the indicator for missing. And you can actually try this out yourself. You can impute it with different values. You can impute it with and as long as you've got that missing indicator there, you'll see it won't actually make a difference. It'll all be in that, that missing indicator will capture it. So what's going to happen here, if you've got 3 different GPA scales, you'll have 3 different, you'll have indicators there for missing, and so you could have, oh, they're missing the 5-point scale, they're missing the 4-point scale, they're missing the 100-point scale. What those missing data are really going to capture, those indicators are going to capture, are partly what school these kids are coming from. Are they coming from schools that use the 5-point scale? Are they coming from schools that use the 4-point scale? Are they coming from schools that use the 100-point scale? And essentially, that's what that missing is going to be capturing. So by keeping it separate, you're sort of coding in an indicator for what schools these kids come from. And that missing variable is going to capture that. So let me just pause there and see if that makes sense.
So I do understand that, and you do retain information that way. But going back to the other question is what is the reason for not recoding, like, you know, taking the 4-point scale and multiplying it by 25?
So I think that it sort of goes back to what you just said there. I think it retains a bit more information if you don't rescale. So if you combine it, you're losing this information about, are they coming from a 5-point scale or a 100-point scale? So you can, that's an empirical question whether that matters or not. So you could try it separately, and you could see, you know, boy, if I combine this, it doesn't really seem to make a difference in terms of how students are placed versus if I leave it separate, so let's just combine it. And I think that's a perfectly reasonable thing to do. So if it were me, I think it's sort of easier actually to leave them separately, but if you felt differently, you could just see, well, does it make a difference if I combine them? We lose a little bit of information, but maybe that makes life easier. And so I think it's reasonable as well. It's just an empirical question how much that matters. And fortunately, it's one that you can actually look at the empirical implications of. So that's how I would approach that. Does that make sense? Feel free to push back if that doesn't make sense.
I understand what you're saying. Thank you.
Yeah. So, and I think we've also, I should say that we did test out, including, going to your point here, we actually tested out putting indicators for where students come from for high school, because one can imagine not only are the scales different, but different high schools, the course rigor, the grades might be harder in some instances than others, right? So a 3.0 at one school might mean something very different from a 3.0 in another school. Interestingly, we found that those indicators for high school were not predictive at all. They added very little information. We'll come back to how we evaluated that. But, again, these are empirical questions, so fortunately, and so one can discern how much this stuff matters. We interestingly found that that sort of stuff didn't matter, which might actually speak to your point that you could just as easily combine these variables, given that it doesn't seem to matter which school they come from. But again, it's something one can test. So yeah, thanks. It's a good question. Okay, so we also have the cohort, the year of admission for the student. So you can observe, are they in, the first cohort of the data, the second cohort, the third cohort, useful to separate that. Diploma status, so for instance, getting a GED or otherwise. There's the years since high school graduation, which is a discrete measure, kind of more or less continuous since it's in years. And then we also included the placement scores as well. So these are typically the variables that we used in the algorithm and how we coded them up. Okay, great. So I mentioned before what we do with missing data. And, you know, ordinarily, if we wanted to look at the causal effect of a variable, we might do some fancier imputation if we want to know the causal effect of, I don't know, high school GPA or something to that effect. But because we want to just know the predictive values, I actually think that this missing data approach is really useful here. So as I said before, we just impute with the mean, create a separate indicator for missing. I give you an example of some code here. I apologize. So I'm an economist, and we've all been sucked into using STATA, which is, you know, quite expensive software. Hopefully you guys are using something cheaper like R, but this gives you a gist of what we do. So, you know, we have the high school data. We generate a missing variable here, so that's what is going on here. This just creates an indicator for missing high school GPA, and then this second line here, we just replace high school GPA with 0 if the missing indicator equals 1. And so that's as simple as the imputation is. And it turns out it doesn't matter what value you give it. So we give it 0, but you could give it any value. It makes no difference whatsoever. It just rescales the coefficient on the missing variable. So there is one key assumption with missing data that's really important to highlight here. And this actually is a bit of an issue for us in the placement study as well. One key assumption of missing data is that it will be missing for the same reason for incoming students. So let me give you an example of where this might hold and how it might not hold. So for instance, high school GPA is a really great indicator, or a good example in this case. So high school GPA might be missing for a number of reasons. Maybe just students can't get it in on time, or sorry, maybe it's just not coded readily in the historical data. So for some colleges, we had to actually go back and work with you to code high school GPA into the data. With other colleges, it was being collected already, but you know, still some instances of missing. So let's highlight a couple of those examples. You know, if the rate of missingness and the reason for missingness is roughly the same in the historical data as it will be in the incoming data, that's ideal, because it means our indicator for missing, that interpretation of that coefficient is still the same. It's picking up the same types of students who are missing that data in the historical data as they are in the new data. But now let's say, you know, we institute a policy that collects high school GPA on the applications themselves. So you have that immediately and you have it for all students. Now there might be very few students missing high school GPA, and when it's missing, it might indicate a very exceptional circumstance. And the interpretation on that indicator for missing might actually be different in the historical data than it is in the incoming data for new students. And that can create a bit of an issue. There's no ideal solution here. I think the ideal solution is just to update the algorithm so that you keep capturing, you know, the rates of missingness and the reasons for that missingness. And you can, if it changes because of policy, you gather the data so that you can update the algorithm accordingly, and you do the sort of the best you can do. But this is a sort of one of the assumptions behind missing data that's important to keep in mind. So let me pause there to see if that made sense, that example, or if it'd be helpful to come up with another example that might show what I'm talking about here. Okay, great. All right, so let's talk a bit about estimating the algorithm, and in particular, estimating the algorithm under some of the implementation constraints that might occur. So potential constraints, you know, how will placement actually be implemented, meaning sort of what can actually be programmed in so that you can generate a placement indicator quickly. So you know, one kind of basic thing is, say you run a nonlinear model, like a logit model or probit model. Do you have a way to input incoming student characteristics into the coefficients that are generated by a logit model or a probit model, a nonlinear model? That might not be trivial depending on how this actually gets implemented in practice. so that's kind of point 2. And then point 3, if you're using the AccuPlacer system like we've done with colleges, integrating this algorithm with the AccuPlacer system, we actually could not use continuous measures. So we had to transform our continuous measures into categorical measures, so discrete measures, since the only continuous variables that can be used in the AccuPlacer system are the exam scores. So we'll come back to that point 3 shortly, but we're going to start with actually just a simple linear probability model. So this is just a linear regression that we'll be using. And this was because of one of the implementation constraints we face is we could not readily implement a nonlinear model like a logit or a probit model. What we did, though, is we compared what did placement look like under each of these models. So let's say we could run a logit model or a probit model, and then we placed students using that model. Did it look all that different from placements using the linear regression model? And so we could compare both of those, and we found that it actually didn't make a heck of a lot of difference. It didn't change that many students' placements. And so we felt pretty comfortable with the linear probability model. And, you know, one can do that sort of comparison for other reasons as well. You know, if there's other constraints that come up, you can say, well, what's the ideal model and how does that place students? Now let's compare it to this model that's kind of more constrained, what we can actually implement. Does it result in a lot of different, does it place students that differently? And so I think that's kind of one good benchmark to think about when looking at, you know, doing placement under these sorts of constraints. Any questions about this simple setup? Yeah, please.
Yeah, I do. For number 2 there, why use a logit or probit model? Why not logistic regression?
Why not a logistic regression? Is that what you said?
Yeah.
So logit model would be the logistic regression. So those are the same. They're basically nonlinear models that are meant to capture probability, so that your output is strictly between 0 and 1. So the logistic regression, it will be the same as the logit. The probit model is another nonlinear model that is used for these sorts of probabilities. It assumes a normal distribution. The logit assumes a logistic distribution, but they usually end up with pretty similar coefficients or predicted probabilities, I should say. Yeah. Any other questions on that? Great. So we're going to start with a linear probability model. You know, I think a lot of the same sort of processes will be the same if you chose kind of a fancier model. But you know, to make sure that we can start with something that everybody is more likely to be able to implement in general, we're going to start with this linear probability model. One issue with linear probability models, which goes back to what I was just talking about, is they can actually produce probabilities that are greater than 1 or smaller than 0, which is a little odd, obviously. Given that we know probabilities are, either between 0 and 1, it's not really such an issue here because, you know, we're just going to come up with a cut point where people who are above a certain probability are, we place them into college level, and people who are below a certain probability, we don't. So keeping it between 0 and 1 is not actually all that essential here, even though in general it's nice to have probabilities that make sense just from a conceptual standpoint. Anybody have any questions just about that little point there? Okay. All right, so, you know, in running a linear probability model, one question is what makes a good model here? You know, how do we assess model fit? And there's actually several ways of going about this. I'll talk about a couple of common measures, but there are fancier measures that, you know, you can use as an extension, cross-validation and machine learning type of techniques, but we're going to stick to 2, which I think, capture things pretty well. And if you want to get fancier, by all means, certainly. So one way of deciding a good model is how well does it sort of fit the data? How well does it capture the data here? And a couple of well-known measures are the AIC. The IC stands for information criterion. The B is Bayesian information criterion. The A is Aikike, I think is the pronunciation. I could be butchering that, so I apologize. Information criterion. They're pretty similar. And what they do is they're a function of the likelihood. And likelihood, without getting into too much of the details, is sort of the likelihood of the data occurring, and how are we choosing parameters, are we choosing coefficients that seem to maximize the likelihood that we observe the data that we observe. And so that's why it's called the likelihood function. It's based on maximum likelihood estimation. For a linear model, the maximum likelihood estimation is the same as the ordinary least squares model, which we're dealing with. But let me sort of get to the punchline here. The AIC and the BIC, so they want to maximize sort of the model fit. You can think of the model fit as being this term here, how well it matches the data. And then this K here is meant to be the number of variables you put in here. So that's when I say I use parameters in, sorry, there's a typo here, parameters and variables interchangeably. And so one thing is that if you include more and more parameters, if you include more and more variables, mechanically you start to fit the data better, even if they're not, these additional variables aren't all that predictive. So if you just include a whole bunch of indicator variables, even if they aren't all that meaningful, you'll start to be able to fit the data better. Sorry. And so what this K is doing is sort of penalizing that fact. It's putting a penalty for the number of variables you put in here. So that's what both of these do that. And so one thing to keep in mind for both of these is that a smaller value is actually better. And so you can see the K is positive. So the more K, the larger the value you get. So that's sort of the penalty term. The main difference between the AIC and the BIC is that it scales this K by the number of observations you have here. And so it puts a little bit more of a penalty on the number of parameters you have. So in practice, we don't find all that much difference between the AIC and BIC when comparing models relatively. But if you're interested in what the difference is, the BIC puts a little bit more of a penalty on additional parameters than the AIC does. So these are two common measures of model fit. And again, smaller value equals better fit. So you can run a model, with a bunch of characteristics. So we might have a model that has high school GPA and indicators for what high school students come from. And we run that model and we get the AIC from that model. Then we might have another model which has just high school GPA and doesn't have those indicators for what high school students come from. And we look at the AIC for that model. And we can then compare, okay, which of these models seems to fit the data better? Which one has a lower AIC? And we might actually, what we tended to see is that the model without the indicators for what high school came from had a lower AIC. The penalty, this penalty term here for adding indicators for high school GPA, or sorry, indicators for what high school students came from, was outweighing any benefits that we get from additional model fit. So that's one way we compared how well the models were doing relative to each other here. So I'll pause in just a second for questions. There's another way you can look at it too, which is this adjusted R-square. And it's important, so this is an okay measure. One thing is that it's really important that you use the adjusted R-square. And what is adjusted R-square? The adjustment here is that it adds a penalty term for the number of parameters, which again is this, it's done for the same reason as I said before. If you just add in a whole bunch of variables, even if they're meaningless, you will mechanically increase your R-square. Just the more parameters you add, you will do no worse in terms of R-square than if you didn't include those variables. So if you use the R-square, make sure you use the adjusted one, which has a penalty for the number of parameters. So let me just pause here and see if there's any any questions about what I'm saying here. And I'll show some example of a code that we used in STATA in just a slide or two. Any questions about this? Okay, great. So I'll get into some more specifics here. Okay, great, in just a few slides. So as I said, we start with the linear probability model. We do a separate regression for each subject. So the left-hand side is an indicator for passing the college level course. The right-hand side are all the covariates that we think might be predictive. Importantly, you want to think about when you're playing around with models here, in comparing them, is you can think about interaction terms. So maybe you interact high school GPA with time since graduation, and you can assess, does that have any informative value? You can also think of higher order terms. So what's higher order mean? That's just a fancy way for saying we're adding the square of a term or the cubic of a term. So maybe we want to look at high school GPA squared, high school GPA cubed, that sort of thing. All of these are terms you can add in or subtract and see if that helps fit the data better based on these criteria I just discussed here, the AIC and BIC. If you want to get fancier in terms of extensions, as I mentioned, there are techniques which sort of are automated processes to select the covariates. There might be even some packages, I think, in R that might do this for you. I'm not immediately familiar with them. In the end, you know, what was interesting is we didn't have that many variables to choose from. So, you know, I think the machine learning techniques really come into play when you might have 100 potential variables or, you know, maybe 30 potential variables that you could choose from. And you could get to a high number of variables if you start doing a lot of interactions, a lot of higher order terms. We found that those higher order terms didn't really seem to add much, but I encourage you to sort of see that for yourself and to what extent that's true. So, you know, I'm not sure the machine learning techniques really will have that much additional value unless you start introducing transcript level data from high schools or something to that effect. So I'm going to keep pushing through here to make sure that we can stay reasonably on time. But okay, so what we're going to do is run the regression on the sample who took the college level course first, as I mentioned before. And so here there's this is where the extrapolation comes in. We're going to, once we have the coefficients from that regression, we can predict what is the likelihood of success for everyone eligible for placement, even if they weren't originally placed. So it almost gives us, you know, this sort of counterfactual here. So that's kind of the two steps we're going to run. One thing I encourage people to do is to hold out some of the sample here. So when we run the regression, don't do it for the entire sample. Hold out, for instance, one cohort from the regressions here. And what this allows you to do is provide an additional validation of the models because you want an out-of-sample prediction. The ideal for these types of techniques is you choose some data set, and this is what they do, you know, when they're trying to predict your, you know, when Netflix is trying to predict what movie you're going to like next, they'll actually do the same sort of process. So they'll choose a sample of folks where we'll run the regressions and sort of figure out what the best regression is on this data set, and then they'll test it on another data set where that they hadn't sort of touched before. And so that's what we're going to do here, or what I suggest doing is, so say we have 3 cohorts, hold out one of those cohorts, for instance, the third most recent cohort. Run your regressions, assess your regressions, your model fit on the first 2 cohorts. And then you can run the prediction on the third cohort and see, well, how well does this algorithm seem to do out of sample in this third cohort here? So, you know, we generated these predicted likelihoods of success. Does it seem to match the actual success pretty well for that third cohort here? And this helps avoid this overfitting problem that can arise if you didn't do this. And it hurts your ability to predict out of sample. So let me just pause there and see if there's any questions about what I just said there.
Yes, at our school we have so if we took math, for example, we have a very large proportion who are not placed at college level, like 75%. So does that impact the efficacy of the model, since you're only testing with the students who are placed at college level? That's only 25% of the population.
Yeah. So, I think there's two aspects in which it could impact the estimation. One goes back to this extrapolation issue, which I mentioned before. So, I think that's, as I said, that's mitigated somewhat by the noisiness of the AccuPlacer exams, and there's not a ton that can be done about that. The other aspect is that it directly impacts is the sample size, sort of like how many students do we have to estimate the model on. And the only thing that can solve that is trying to get multiple cohorts of data, of historical data, to gather up a decent sample size. As I said before, there's no kind of strict rule of thumb for what's kind of quote unquote enough sample. More sample, I think, is better strictly. But and maybe, sort of the best one can do with that is see, well, if I were using just half my data, do the coefficients seem to change a lot than if I use all of my data? It can sort of give you a sense for how sensitive the model is to the number of observations. Unfortunately, I can't sort of provide a hard and fast rule of thumb there, other than to say, try and get a lot of data to the extent possible. Does that answer your question? Okay, well, hopefully it does. Okay, so here I'm going to show some code which we used in the data set. I'll run through this relatively quickly. This is using STATA code. And so again, apologies if you don't use STATA. But first, we run the regression, an example of regression. This is for English placement. So we've got, this is running a linear regression here, an indicator for passing in English. And so this is our outcome. And these are all our covariates here, everything we're going to use to predict. And so we've got their high school GPA, an indicator for missing, their AccuPlacer score, their when they graduated and diploma status, et cetera. And then we make sure that this regression is only being run on those who took college first. We're holding out our third cohort here. Like I said before, we're not running it on all the cohorts so that we've got one sample we can test on out of sample. And for us, we wanted to make sure we only did this regression for those who are eligible to be placed, which in our case here means that they took the placement exam. So these are sort of all the conditions that we talked about before here. So we run this regression. This is just a least squares regression. We can then predict the probability of success for everybody once we have the regression. So this generates a prediction, a probability of success for everybody in the sample, even those we didn't run this regression on. We still restrict it to those who are eligible to be placed, meaning that in this case, they took the placement exam. And then there's a nice way to export results in STATA. And so we export all the coefficients here. That's what's going on in this. And we export some statistics. So the R squared, the AIC, and the BIC. And this will allow us to compare our models across each other. So does that make sense? Let me know if there's questions there. And so what we can fiddle around here is with the covariates that we include up here. So we can change the covariates here. We can add interactions, higher order terms, do variables, et cetera. Okay, so moving on a little faster here. As I mentioned before, use the AIC and BIC to compare models. Use it based on the first two cohorts. And then allows you to do some out-of-sample predictions and assessments of the model in cohort 3 here as well. So I'm just going to keep moving a little bit here. Okay, so one thing to keep in mind for AccuPlacer, and Dan will talk about this with each college, how he did this for AccuPlacer. But as I mentioned, all covariates must be categorical for AccuPlacer. So the biggest constraint here was that GPA had to be in years since graduation turned into categorical variables. So we might have indicators, you know, you might bin them up into terciles for GPA or graduation, so that you create a categorical variable with you know, with a couple of values there for GPA. And then the rest of the estimation procedure just proceeds exactly the same though. So instead of having the continuous variable for GPA, you've got dummies for each tercile. So when I say you make it categorical, I should be a little more nuanced there and say that have dummies for each category. So you know, you don't input it as though it's a continuous variable. You make sure you have dummies for each category here. So you might have an indicator for GPA, GPA in the tercile 1. I don't know why this is giving me crosses. So that's one variable. And then you'd have another variable, which is GPA in the second tercile. That's what I mean by dummies for each category. But then the rest just goes as the same. And, you know, given this constraint, you might want to know, well, how is this affecting the model? You can compare this binned model with your unrestricted models. You can compare it in terms of the EAIC and BIC, but you can also see, well, how many placements does it change as well? So you could create a variable which you look at the placement under one model, the placement under the others, and just count the number of times those are different. So that's one way to do this here. Okay, so let me keep moving along. Elizabeth, are we supposed to, I apologize, we're supposed to conclude 11? Yeah, all right. So I'll just finish up with, I think this is actually probably the last really important point. So decision 3 is choosing a good cutoff probability. So you might get a whole bunch of predicted probabilities here, which represents this distribution. And then you've got to choose some sort of cut point, this 51% as just an arbitrary example. So everybody with a score of 51% and above gets placed into college level here. So, you know, there's various things to consider. What are the average pass rates among those you place into college level? What's the number of students predicted to be placed into college level? And what are the number of students predicted to be placed in remedial? These are all things you might want to think about when you're choosing a cut point. So let me just give you an example here. So this is a spreadsheet. So let's say we've chosen a model, and then we can look at, for all of our cut points that we choose, so this is examples of cut points. So if we chose the cut point at 45%, this would place 70% into college level. We can look at what the percent of our expected to pass are, which are, in this case, it would be 60%. And then we can, you know, based on this fraction here, we can see how many people would be placed into college level given what we expect the cohort size to be. And then we can allow, you know, we can give this information back to the colleges to say, hey, how do you want to choose your cut point? A lot of the colleges wanted to hold the pass rate the same. So in the historical data, they might have seen, well, our pass rate in the past was 63%. Let's make sure that that's still the same. So let's find that here, 63% pass rate, and that gives us a cut point of 51%. And what's interesting is that in the historical data for this hypothetical example, the placement rate was 40% into college level. If we use the algorithm, we actually expect we'll get a 56% placed in the college level. So we're expecting to hold the pass rate the same, but place more students into college level. So we think this sort of spreadsheet is useful way to summarize the information you get from the models to help choose a cut point here. Okay, so I can wrap up here with you know, how to update the models really quickly. The key thing to consider here is that if you're updating the model, you can just add new cohorts and rerun this same process as we did before, you know, comparing model fit with the new data you've got. Maybe the coefficients might change a little bit. So that's, you know, if you get new data, that's one way to do it. If you want to include any new measure here, sorry, I don't know what I've done there. the key is you've got to be able to link this new measure to the outcome being predicted. So that means you're going to have to develop historical data with this new measure. So if you run a survey, you're going to have to run it for at least a year, probably more, so that you can link that measure up to how well it predicts the likelihood of success in a college level course. So I think I'll stop there. I know some of you probably have to jump off. If you have questions, I'm happy to hang around now for a few minutes and answer those. I think we've talked a lot about the limitations already in terms of extrapolation and AccuPlacer exams being kind of noisy here. So I don't think we have to talk too much about that. But thanks, everybody, and I'm happy to stick around for questions and happy to take those by email as well, too.
Yeah, I just want to ask, how do we get these slides? How will those come to us?
Beth, you probably have everybody's email, at least that signed up, so you might be able to distribute them. Yeah. So anyone who registered, we can provide this to, and I don't think there's any issue for those. I mean, you can also email us directly if we don't have your email address. And I think we pressed record on this webinar, so we'll also be able to share the recording as well. And you know, do feel free to email me with sort of other questions as well. I'm happy to sort of try and answer those.
Could you give us your email? What is your email?
Yeah, absolutely. I'll write it down here if this actually works. There you go. So it's tc.columbia.edu, and that's my last name, Bergman @ tc.columbia.edu.